Hello. We're getting into some good physics stuff today. Not that we don't every day, but we're getting into classic physics stuff. These are called Atwood problems or problems with multiple bodies, and this is just a complete requirement if you take a physics class. So what we're going to be dealing with is typically two bodies, one big M, one little m, connected by a string. And typically the game is to figure out the acceleration of the system and to figure out the force of tension that's in the string between them. And there's two ways that you can do these. I'm hoping that you get the easy way, and there's a link that I'm going to post where Khan Academy explains how to do this. So the first way what we'll do is we'll draw force diagrams for both the masses. So and we're defining acceleration as positive is going to be in the way that the thing is going to move. So the way that it's going to move is to the m is going to move to the right and little m is going to move down. So that's positive. So so for the big M, we've got the force of gravity down, so equals a big mg. You've got the normal force up, and you've got the force of tension to the right. We know that the mass is only going to accelerate to the right, so the normal and force of gravity forces cancel. They do not have a net effect on anything. Then moving over here to the little m, we've got little mg force of gravity down, which is going to be bigger than force of tension. Now remember, this force of tension is the same as that force of tension from Newton's third law. So defining a Newton's second law equation, so mass times acceleration equals the net force. So these two forces cancel, and this is going to be my net force, F sub t. So mass times acceleration equals net force, which is F sub t. So that's our first equation, which is a nice easy one. Then for our second equation, we're going to define mass times acceleration, because it is going to accelerate, the forces aren't bounds, equals mg, which we made positive because we said down was positive, minus ft, negative because we said up was negative. So now we said that this is the same F sub t, so what I can do is substitute in F sub t for ma, and do a little simplification, and what we get is that the acceleration equals mg over m, little m plus big M. Now this brings us to the second way of doing this, where we can kind of jump to this with one step. So what we can do is draw an imaginary box around our system. And any force that crosses through this box, that doesn't look like a box, my line, okay, that isn't canceled out gets written down. So so let's see. Let's look at this one. Is there any force on this one that isn't canceled out that crosses my line? Well, the force of gravity and the normal force are canceled out, so I don't have to worry about them. The force of tension, that stays within my boundary, so I don't have any forces to worry about here. Okay. Now if we look at the little m, the force of tension, that doesn't cut through my box, so we're not going to worry about that. So the force that we're going to deal with is m times g, and that's positive because we said positive is down. So and we put that on our forces. So acceleration equals force over mass. So the forces go on top and the masses go on bottom. So the only force that's going to cause the system to accelerate is little m times g, and the mass of the system is little m plus big M. So you can kind of jump to this equation, skipping the force of tension route, if you kind of draw that imaginary box. Let's work another one. Are there any questions? And there's no questions? Good. You guys all got this. And this will seem a little, awkward at first, perhaps. Wouldn't be too surprised. Here we've got another system. This time, instead of having it on a flat incline, one of them on a flat incline, we've got them both on over a pulley, and we've got little m and big M. And what we want to do is figure out the acceleration of the system and the tension in the string. Okay, so typically what I'm going to do is I'm going to start out with free body diagrams for both of the masses. Okay. And then we'll solve it both ways. We'll solve out for f sub t, and then I'll show you how we could have just jumped to the final equation. So force diagram. So little mg down, force of gravity down on this mass. Force of tension going up for that mass. Now this system is going to accelerate, so we're not going to say the forces are balanced. There are no forces in the x direction, just in the y direction. So mass times acceleration equals ft. Now we're gonna, I guess I should have said this, we're gonna consider the system positive direction in the direction of acceleration, which means it's gonna be up on the left side and down on the right side. So that's important. If you mess up the signs, then it gets wonky. So up on the right side, up on the left side, down on the right side. Okay. So on the left side, f sub t is positive, okay, because left up is positive, minus mg. So that's our mass times acceleration equals net force equation. Okay. Then on the right side, we've got big mg going down, and we've got ft, same ft, going up. So writing our ma equation, big Ma equals big mg minus f sub t. Okay. Now again, mg is positive because we said on the right down is positive, and the direction of acceleration is positive, and ft is negative because it's up. Now substituting in for f sub t, solving this for f sub t, and then substituting in, we get this. Doing some math and some solving, we get that the acceleration equals big mg minus little mg over little m plus big M. My m's don't look very different here, that's unfortunate, but little m plus big M. Now we could have drawn our box around our system here, and we could have said we're only going to take into account forces that cut through the box. We still want to say that to the right is down is positive, and to the left up is positive. So the forces that are going to cause it to speed up are positive, basically. That's really how it works. The forces are going to cause it to speed up, which is going to be big mg. The forces that are going to cause it to slow down, opposite that it's going to accelerate, we subtract. So that's little mg. And then you divide by the total mass. So m plus big M, little m plus big M. So if you can see it, I'm not sure, how good you'll be at seeing it right off the bat, but if you can see it, it saves you quite a bit of math. If you can just kind of jump to that step. Okay. All right. So again, the big mg is accelerating it. Little mg is trying to slow it down. It's opposite motion, and then we divide it by the total mass. So that's kind of the other way of doing it. It's just gonna. Oh, sorry, I didn't realize I was still recording. I thought I had it paused. So throwing some numbers into it. So big M is 12, little m is 10. You get that the acceleration is going to equal 0.89. Then what you have to do, once you figure out the acceleration, is you have to go back and pull one of these equations. It doesn't matter which one you use. I think I probably pulled the left one. And so now we're going to stick our what we know into that equation, 10. We now know A is 0.89. We're looking for F sub t. Little m and g we both know. And you get that the force of tension is equal to 106.9 newtons. So we look at the system as overall. We look at the system as a whole overall. And then to find the force of tension, we have to go into one of these equations just for a mass. Okay. All right. Moving on to an incline. So you do them the same way. Hopefully that you've been working on some of those incline problems so that this is a little bit familiar to you at this point. So let's look at it. So we've got big M on the incline. We've got little m over a rope and a pulley. And what we want to do is start by drawing our force diagrams, and then we'll try to just look at it overall. Okay. So we're also going to define acceleration in the positive direction as it going down the as if little m was sliding down. If it ends up that it'd be going the opposite way, our acceleration would just end up negative, and that would be no big deal. But that's the way we're going to assume that it's going to go. Okay. So we have to do the turning the table method, or turning the tilting the page method. We draw our mass times gravity, our force of gravity down. So I just wrote big mg, force of gravity equals mass times gravity. Then we've got the normal force, and then we've got the force of tension. The first thing we want to do is break apart gravity into its components. So that's why I've got a down component and a left component. If I'm looking at the page tilted. We know that the normal force and the force of and the mg cosine of theta is going to cancel, and we that's about all we know. So if we look over at the little mass, we've got mg cosine or mg, just mg, the force of gravity down. And we've got the force of tension up. Okay, so we're going to draw. You could write the equations for these individually and solve for f sub t, solve it out. But I'm just going to kind of practice jumping to the end here a little bit. So picture me drawing my box around this. Okay, so let's see. The normal force and this component of gravity are going to cancel. Okay, the force of tension doesn't cut through my box, so it doesn't matter. Mg cos or mg sine of theta, that's gonna cause an effect. That's gonna cause my system to slow down. That's opposite my motion, so that's gonna be negative. So if we look at over here, we've got f sub t. That doesn't count because it's within the confines of my box. Mg, gravity cuts through the box, so that is going to cause some acceleration, or so that is a positive effect because that's down is positive. So our net force of our overall system is mg. Okay, this component we ignored ft, we ignored these because they cancel out, minus sine of theta mg over total mass, little m plus big M. Now, if you wanted to write individual equations, these are what those equations would be, but we don't need to do that. Okay. And this is one more example I want to go through. So here we've got two boxes, and they're being accelerated upwards by a force of tension, tension 1, T1, and we want to figure out the tension in each cable. We can do the same thing where we draw a box around our system. So we've drawn a box around our system, and the acceleration is going to equal to the net force over the total mass. And so I've drawn my force diagrams here. For the little m, I've got the big tension up. I've got little m, g, and I've got tension 2 down. And for the big mass, I've got big mg down and and T2 going up. So what we're going to do is look at the forces that cut through the box, my quote-unquote blue box, and we'll add the forces that are up, because we're going to consider up positive because we're accelerating upward, and we'll subtract the forces that are negative, that are down. Okay, so so first off, T1, can I ignore T1? No, because it cuts through the box, so I can't ignore that one. That one's up, so it's positive, so we put that one first. Mg2, can I ignore that force? No, I can't. It does cut through the box. It's downward, so we're going to make it negative. Little minus mg. T2, can I ignore T2? Yes, because it doesn't go through the box. It's an internal force. Now moving on to this force diagram. T2, we already said I can ignore. Big mg, I cannot ignore. It cuts through the box, and it's down, so I make it negative. So minus mg, and divided by the total mass of little m plus big M. Okay, and if I had 3 masses, it'd be little m plus big M plus whatever m. And that is, I think that's where we're going to leave off for today. Oh, here I'm solving it with numbers. I guess I gave numbers on it, so yeah, I did. So anyway, so the little, again, 10 and 12. If the acceleration was, so basically what I can do is use this equation to find the tension in T1. So I can find that T1 is equal to 245 newtons. And then I can find T2 by using one of my equations. Let me go back up to one of these equations, so the simpler one is this one, big MA equals T2 minus mg. So I can use that equation to find T2. So again, if this makes sense, that's good. If not, come to my office hours or look at the video that I've got posted from Khan Academy. I'm hoping that made some sense to you. Work on the problems. You can do 3-3 now, not just basically everything but the very last worksheet. And good luck in your studies.